do my application, putting my object in and trying to do a match, and then putting it back in the cluster, I'm going to have the cluster do all the work. I'm going to use that communication. Okay, so it's a pretty simple model. We're going to manage all the data in the grid. We're going to, as much as possible, do all the processing in the grid. So adding, matching, all that stuff's going to happen in the grid. I'm not going to do any sort of, my client's going to connect and cache and maybe put some stuff, but it's not going to really do any work. It's going to instruct the grid to do the work. I'm going to let the grid look after recovery, and applications won't have to do any exception management. That's it. Okay? Right. Now this is where it gets scary. Demonstration. Is everyone awake? Does everyone want a drink or a coffee? How much time we got?
I'd say about half an hour here.
Easy.
Okay.
Yeah. If you want a break, we're going for an hour. If you want a break, grab the water. I'm going to get on the water myself. I'm quite happy for it. Just get coffee.
Anyone want a break? Or straight through?
Straight through?
Straight through? That's the consensus.
Okay, demonstration. The demonstration. So, what I did, I just used clips, and I'll just need to change a few preferences here. So, let's go and have a look at a model. So, I have the concept of an order, and my order has an ID. It has the market at which I'm placing the order. The trader ID, I'm just using UIDs here because I want it to be nice and unique. And the time the order was placed, because often orders have priorities. Like you must match the most recent last, or this FIFO, or LIFO, or all that sort of nonsense. Which side are you on? Are you a buyer or a seller? How much are you going to buy, the amount, and what price? So, an example of an order would be, I want to buy Oracle. I'm in the, I've got a particular order ID. The market is the Oracle market, if you like. The trader might be Cameron, the time placed whenever I created the order. The side is a buy. The amount might buy, say, 1,000 shares, and the price I'm going to pay 10 whatever. $10, 10 pesos, 10 units. So there's a few things here. As I said, objects need to be serialized. So you can use Java serialization. It's fine. It's about 6 times as slow as coherence serialization. Your choice. And nothing bad against Java serialization, but it's designed to handle serializing object graphs. It's designed for handling, multiple structures in one big blob that all have references and all this sort of stuff. That's typically not what you see with these sorts of systems. You serialize them with single objects. In fact, we'll actually show you in the market, I'm serializing a whole big object. But the serialization that Coherence provides, it's just an interface called externalizable light. It's optional. If Coherence sees your objects that implemented this, it will default to using it. Otherwise, it will fall back to using normal Java serialization. It's just faster. Produces less garbage. It's great. Smaller on the wire. Great. Faster to produce. Not mandatory, but you can. I've just decided I'm going to go the whole hog here and implement it. The rules for externalizable light are the same for serializable. So you have to have a serialization ID, you have to have an empty public parts constructor, and then this is my standard sort of constructor. Market ID, the trader, decide the amount of price, and we assert that you're not trying to have negative prices or negative amounts or zero amounts. You can't buy anything for zero, and you can't buy nothing for nothing. Okay? So this is pretty much like a usual sort of project. And it's a real project, because I know we're not going to do any magic around it. I'm not going to inject some AOV around it. I'm not going to cover it and wrap it. It's just this object. So any optimizations you make to methods or any representations of data in this object, it's yours. Variance won't touch it as they are. And then, the last bit is, well, coherence deals with data streams, not object streams. So it's pretty much like you have to write this stuff out. Now, it looks pretty open, and yeah, it is open. You write it once. Write it once and then write it again, really. There are some annotation-based, I've got some examples of how you just use annotation with JavaWUG, and magically does it all for you. But there is a cost, because it has to use reflection to do all the work. And I'm talking about a trading system here, so I don't particularly want my trading system slowed up while it's reflecting what it feels to write out to a string. Is that money? No. Every time I use reflection, I'm throwing money. I want all the money. Right? Because it's time. Time is money in the trading system. Okay, so that's an order. Aside, pretty simple, it's just an enum. And I've written some externalizable helpers here for so I can externalize these things. That's fine. What is the concept of a trader? Well, trader has an ID and a first name and last name, and again, so relatively small prices. Most of this can be generated with clips or IntelliJ wizards. The only bit that I really had to write was the read and write externalizing stuff. Probably should make a plugin for clips to do that as well. Generate serialization. Something from IntelliJ wizards. A fill is a trade. So remember I talked about a trade or a fill. That means that there's been some agreement on the buy side and the sell side. So we've got a market that I've agreed the order ID that you're buying, the order ID that you're selling, the amount and the price between those two. Because there may be a partial fill. Maybe only a piece of my order is settled. Okay? Not everything matches perfectly. So John and I always say we're both going to buy 10 units of Oracle each, but someone is selling 100 units, so we could both match against that other person. Okay? Again, it's externalizable. I need the usual thing, so it's just another project. So I've done a fair bit of the work. I've almost built my trading system. So where is all the mess? Where is the nasty bit? Well, it's in here. So this object, which is just a plain Java object, represents a market. So it has the market ID and the name of the market. We need to know, so what I'm doing, this is classic OO programming, right? I'm not breaking stuff into service beans or anything else. It's just Pojo, classic OO programming. Market ID, then I've got all my sides. I've got all the guys that want to buy and all the guys that want to sell. People will buy and sell. And it consists of a map from price, which is the music track, to all the people on the side. Because I need this data structure that says, there's a whole heap of people that want to buy at one price, and there's a whole heap that want to sell at one price. And I have lots of prices. So this is exactly the Betfair model of how that trade system works. So they're all of the people that are buying and selling. And then I'm keeping some little stats variables here. I want to keep what's the volume of this market, because I want to produce some numbers in functional marks. And I want to know how many trades have I processed. So the rest is all, the rest of this is like simple Pojo. So I've got my constructor, I need my empty one, constructor market. When I construct a market, I'm just saying, right, I've created a new market now, and it's got an ID and a name. Everything else should be empty. I've not traded anything yet. Both the buy and sell side should be empty. There's no one here. I'm making a new market up. So imagine that. I'm building a market simply by creating an instance of a Java object. Okay.
So what is the key?
The key will just be the market ID.
The market ID.
So I'll show you the actual working code, which is way smaller than this. Often I want to say, what's the value of the market? And really you ask, what's the value of the side of the market? So how much money is on the buy side of the market? How much money is on the sell side of the market? So I can say, well, total. I'm going to pick the side that I'm interested in, pass to the side. If it's the buy side, I'm going to use the buy side data structure, and I'm going to use the sell side. And I'm going to iterate over all the sides state. That's got my list of buyers and sellers. And I'm going to ask it, tell me what the amount is available multiplied by the price. So this is just going to tell me the amount that's available on the buy or the sell side, which I'm going to tell. Notice I'm using longs. I need precision. You can't use floats. Never use floats. Use big decimal if you have to. Longs is great for representing money. Then I can say volume trading, etc.
So you never consider fractions at all, then?
Never.
No, not at all. Not interested.
It's done in pence.
Yeah.
Pesos.
Yeah.
Some really small currency.
I'm just thinking of Superman 3. It just slips through the crack.
Yeah.
Okay.
Big decimal as well.
Yeah.
Big decimal is classic.
Okay.
It's got precision. So add an order. So add order is where all the work occurs. This does all of the matching. So it says, I'm going to provide a list of fields I've already made. And I've got an order. And this works out how to do the matching. So this bit obviously took me the longest to write because it says, well, okay, I'm on the buy side, John's on the sell side. We've got an order at the same price, right? Then they match. But what if I want to buy less than what John's got available? Or I want to buy more than what John's got available? So all of those conditions about matching in the market are all here. And hopefully they're nicely commented. And it keeps track of it. So that's it. And then there's a read external, write external. That's a little more complicated than before because I'm writing out data structure. The coherence has some wrappers to do this automatically, but I want to make sure I'm just writing out exactly the bits I need. Okay? And then there's some more sort of internal classes here to work out, right? Which side, how many orders I've got, how much of an order I've got, etc. So that's it. That's my market. Okay? So how does it work? Well, we can look at the test cases. And the first one is, the first test. I'm using test.ng. Does everyone use test.ng? It's really good. When you use test.ng, or you go from JAVAWUG to test.ng, it's very hard to go back. You like JAVAWUG.
It's got all the annotations now as well.
It's got some subtle differences in semantics, which makes it good when you cluster it. These are unclustered tests, so I'm not doing any clustering yet. I create a market, create a trader. I'm going to create an order for that trader, and I'm going to buy 100 at a price of 10. Add the order to the market. I should get some fills. I don't get any fills back because the new market wouldn't match anything. So ensure there's no fills. Ensure that the market value on the buy side is 10 times 100. Yes. Good. And there should be nothing on the sell side. So these are just some little unit tests to ensure that when I put in a buy, that it goes into the market, and I put a sell, that goes into the market. And then I can test things like, do I have a perfect match? If I have one buyer and they're both buying and selling, and I put them all in, I should be able to sell both sides. I should be able to close both sides and get one fill back. And the fill I would get back should be the trader who actually these two things at trading. Okay? And then there's a test for imperfect match, but we won't go through that. Okay, so test cases. We just always like to run tests to make sure that they work. Yeah, get the green check that everything's cool so far. Right. So now let's look at the actual code. I want to work through a little bit of coherence. This line is coherence. It says, go to a cache factory and get me the cache called markets. Now, by default, coherence has, and will provide you with caches of any name you choose. You don't have to go to a panel and set them up and just say, give me a cache, I want a cache from you, and it's going to be called markets. It's okay, gives you one. and it implements this named cache interface. Now, named cache actually inherits from the map, and inherits through a thing called, basically a thing called JCache, so it implements a JCache there. Once I've got that, I can do anything like I would usually do with like a map. So I create myself a market object called Oracle, and then what I'm going to do is I'm printing out saying, look, I'm going to try and create this market that doesn't exist. And I can either just say markets.put, so this is a map, it's like a hash map, key value there. I'll put this market object into the cache using its ID. Or I can do something a little more funky. And I'm going to say, well, I'm going to invoke on this map and say where this ID is, where that key is in a cluster, execute this piece of work. So I'm telling the cluster now to execute some work. The first one's nice and easy, but this is just like a show off down here. I want to tell this class with a method in it to go and execute at some point in the cluster. Let's go and look at that. And that's called an entry processor. So what happens? When you invoke, it serializes that request up, sends this code over, so the code's there, sends the request over, unpacks it with the data, and says, right, is the entry present? If it's not present, set the value. So I'm actually going to the primary node where the data is and saying, set this value right here. Now, the cool thing about that is, if I execute this many times, if the market's already in existence, it'll only be created once. So, great. I'm creating the market once, and then I'm just going to wait around. Now, the cool thing is, the life of a cluster is really the life of the oldest member of the cluster. And this is just a JVM. Simply by calling cachefactory.getCache, this app will try and cluster with something. It will try and form a cluster by default. And it uses a variety of techniques. By default, it uses multicast, so it does some network magic to form a cluster. Then I'm going to put some data in the cluster, and then I'm actually going to, I don't want to shut this JVM down, because if I do, then it leaves the cluster. So I want to keep this process running. So I'm just going to do a system read. It's called logic hack. So the only exception that this code throws is an IO exception because of the system read. And then when I hit enter or something, I'll shut the cluster. So this app here, run markets. There's a tiny delay there, because it's timing out. It's going, hey, is anyone there? Sort of walking in an empty room to try and find a friend. Hey, is anyone there? No, no one's there, right? I'm a cluster. So it says create a new cluster, then run in one, and stuff right here. It creates our market, and then it's waiting to do some work. Let's run another one. I'm just going to run another copy of this. Notice there was no delay this time, because there's already a process there which was saying, well, I'm a cluster. This one joined straight away. This is member 2. So now I have 2 JVMs running on the cluster. It's exactly the same progress. So the third one, I can just start them up. Okay? And I can sort of hit enter. Now, I hit enter, which means in this process, remember when I hit enter, the last thing it does is a shutdown? It says, well, look, before I shut down, I'm going to transfer some data that I have, and I need to transfer that somewhere else. And the other processes will pick that up. It doesn't show it here, because it was a graceful shot. But I can start another one with processes now. Now, number 4 start. Okay. Now, let me just really show you that this is actually working. So we're clustering, that's fine. what I want to do is, I've got some code commented out here. When I start up, what I'd really like to do is I'm going to add a listener. And I'm just using an inner class. So the markets is a cache and there's a service which looks after that in Coherence. And I'm saying to that service, look, I want to add a listener on the service. So you can then find out when members come and go. Because maybe your application is interested when knowing when other processes start and leave. So I'm just going to dump out the response. And I'm going to kill the cluster. So obviously I had any data in those, it'll be gone. I'll just kill the whole cluster. Now let's run markets again. It's a bit of a delay. Okay, now it's up. I'll run my second markets app. Okay, there was no, didn't output anything. But if I go back to my other app, hey, it says, hey, member 2's just joined. Welcome, member 2. And if I go over, if I start another one, if I go and look at member 2, hey, member 2 says, member 3 just joined, and member 1 says, hey, member 3 just joined. So I can kill member 1, just stop it brutally. And we can now look at, okay, member 2 says, hey, member 1's leaving. Notice I didn't have to do anything graceful. It said it's detected that member 1 is leaving, and that's right. It tells everyone, the protocol says we've detected that member 1 is leaving, so it sends out a message. Everyone's leaving, and now it's left. Because let's say you do have some application logic where you do want to know what happens when these things don't go. So imagine this if you're dealing with web services. Providing services, and then you know when other services come and go. You can very easily use it to provide a resilient registry of what's happening. And I can go over here and look at, and it's got exactly the same. And not only that, I've got lots of logging saying, well, I've restored the backup of the data that I had before. Okay? Out of the box, I've added one statement to my program. And that statement could be in a servlet. So if you've got Tomcat and you want to cluster Tomcat, one statement. Okay. 5 more minutes. Oh, I'm killing it. Okay. Right. Let's actually do the real thing now. So I've got this program called run orders. And what does run orders do? It gets the markets cache. We're going to trade on Oracle. It creates 2 traders, one's called Cameron, one's called Barney. And I'm going to do 30,000 iterations. It's actually not the number of orders. I'm actually going to place, buy, and sell 30,000 times. And I've got some little step here because I want to actually print out a dot every time I do something. Otherwise, you just sit there and go, this is not good. Next time, I'll have like a Google or something. It's colours. Beautiful. So, and I've got this thing called a stopwatch, which is a little app that I've written, a little class that will take, with minimal effect on the JVM, take time slices. So, we're going to start this. We create an order to buy, an order to sell. They're perfect. So we're going to buy 1,000 at 10, sell 1,000 at 10, and I'm going to invoke into the market place. I will use this entry processor to buy and sell. I kind of hold this using Java 5 bars at here, and then I'll stop and put out a dot. I'll do that 30,000 times. Okay. So it's doing these little dots, and notice it's slow. It's not because the Mac was slow. It slowly gets faster. It's using the server JVM. The server JVM optimizes garbage collection. Did you see it faster? I've got some graphs here that show the difference between a client and server JVM. Client is completely predictable. It will just be wait garbage collection, wait garbage collection. Server will do a whole heap of work, and the gradual just gets flat out. So I've placed 60,000 orders. So 30,000 wires, 30,000 cells, average of half a millisecond per wire, and my cost is still low. So I can stop this app. And notice this app was completely different from the other ones. It just joined the cluster and was doing some work with the data. And now that others have said, hey, I've noticed someone's left. Now let's do something nasty to it. Now I'm going to run. So let's make it about 50,000. I want to run a bit more there. Make sure I still got this one. I'm going to run some orders. Now it's placing 100,000 orders, so 50,000 bytes, 50,000 cells. Now while this is in process, I'm going to start another markets console. Let's use the stick. So I start another markets down here, and I'm going to I'm just going to terminate that process. And I'm going to start another one. And I'm going to go to the second one. And oops, I'm going to kill that as well. So now I've killed the two servers that I started, or the process I started was managing the data. Killed both and started two new ones while it was running. No exceptions. There's no jam thing. Let's just keep going. Look at that. Hardly any difference in the orders processed per second. So imagine that in a managing website. It's like, I'll manage my web sessions. Who cares if Tomcat or Resin or whatever? Who cares if it dies? And just states managed and just keep going. So the whole lot of things I can show you as well. Just for now. So the state was completely managed within your cluster. All of the executions that were occurring against the data, completely managed, even while they were failing. So let's finish up. What does this mean? What does it all mean? Right. So I promise you, this is what happens. This is throughput in milliseconds if you're running the client. These spikes here are due to garbage collection, nice and uniform. With server, it looks like this. Notice like the average throughput on the other system is really high, just using client. Simply moving, same memory specs, same machine, same test, simply moving around many times to server, you just get massive throughput. Parallel GC, even. So lessons. This stuff is infrastructure for application state. You can build stateful applications that are reliable, even while you're shutting stuff down, while you're doing transactions. It's why they call it extreme transaction process. I don't have to use any transactions to do this. Work was guaranteed to occur. I didn't use two-phase commit. I didn't use any locking. It just works. Didn't use a container. No SVs. I can use it within a container. Nothing against containers. I can use it within a container. Plug it straight to Strip in the Spring. Use data grid beans. The same thing happens. No coupling. There was no coupling between the services. The matching market service. I didn't specify that without joining. I didn't have to say this is a special process that I'm doing that. There's no coupling, not only between the services as software concepts, but also between that and the hardware. Everything's actually transparent. You can just, this stuff moves around. The services, failover recovery. Didn't have to do it with my app. It's a very simple API. It's map plus some extensions. You can do queries, you can do, and all of that stuff keeps working. You're doing a query and suddenly the machine dies, it just keeps going up. You pick up, recover, and keep moving. So this is why they find coherence is used. I said in the survival and the abstract. Why do companies depend on coherence? Especially things like trading systems. It's because of this. I've got a comparison between these sorts of things in terms of what their goals are. Clustering, the goal is availability. usually through master slaves. Grid, slightly different. Data grid, slightly different. I'll let you digest those. So, focuses on the paradigm is focusing on data management, not service management. The data is actually the service. The availability of the data lets you perform services, not the other way around. You execute services where your data is. Petitioning is key. Consensus of cluster membership is key. Without those two things, then you have to use a service-oriented model. You have to manually look after all the services, or have a container or an ESB that does all that for you. So we get back to the whole SOA idea. In the picture, coherence is really your data infrastructure for your SOA. It doesn't compete with SOA, it's a part of the big picture. You can have a bunch of services running wherever you like, but they're all maybe working on this one set of data, and that's where solidity fits. Coherence can also do services, so matching, for example. But it's really infrastructure for things like SOA. Or it can be complete SOA if you like. So hopefully, it's like this.